Okay. So far we have discussed about PDs and so on, semi-group properties, and how do we link our PDs to our semi-groups. So now our main objective is to basically uh, construct solution space for PDEs, and this solution space of PDEs is basically what is called Sobolev spaces. So no matter what your algorithm, say you're solving a PD and your algorithm, basically you feed your PD to the algorithm and it kind of gives some solution U for some PD such as equals to 0. What is the guarantee that the U that you get is a valid solution or not? So that you kind of test, you check if your solution that is generated by algorithm belongs to Sobolev space. So now to construct Sobolev space, it will take some lectures. For that, we first go to convolution of functions. And after convolutions of functions, we try to go to we construct convolution of distributions, and after convolution of distributions we kind of go to what does a fundamental solution mean, and from fundamental solution we go to Schwartz space, and after Schwartz space we go to Sobolev space. So with that, I think I'll end the PD part of that, the abstract things that are going right now. Recording, right? Okay. So now you have F and G, Borel measurable, and so F of x minus y, G of y is Borel measurable, and say if F comma G are integrable, and basically your Lebesgue and Borel measures coincide on Borel sets. Okay. So this is something that most of engineers don't know. So if there are any math people, for them I just want to give this particular definition, but engineers, you can ignore all these definitions. So now let us take, let F belongs to L1R Rn, and G also belongs to L1 of Rn. Implies F integral F of x minus y G of y dx dy is less than or equals to norm F, norm L1, norm G, norm L1. Implies that F star G defined by this integral Rn. I mean, this particular integral is well defined because it is bounded above. Okay. And by the Fubini's theorem, your f star g defined by the map integral f of x minus y g of y dy is well defined. So now we come to definition of what does convolution of integrals mean. Convolution of functions, not integrals. So f star g equals integral Rn to f of x minus y g of y dy, which is basically a function of what? H of x, right? So this is called the convolution of functions f and g. So some properties of the convolution is that one is f star g equals g star h, and next is f star g star h is equals to h star g star f. These are some identities that you get by simply changing your order of integration, and this I'll just leave it to you as an exercise. So now I'll just state a theorem without proof. I mean, or else I'll prove this. So what's a theorem? So if f belongs to L1 of Rn and g belongs to Lp of Rn, implies f star g is well defined and further it belongs to Lp of Rn, and further norm on f star g, norm Lp is less than or equals to norm f L1 into norm g into Lp. Okay, I'll just skip the proof of this, it's kind of easy. These are some theorems that, I mean, I don't want to go to that kind of mathematical rigor where I just drive people away. We just require the theorems. Some mathematician, let us say some credible mathematician has proved those things. So further, if f comma g are continuous functions with compact support, then f star g is well defined. And further, if you just take continuous functions f1, f2, so on till fn, continuous functions with compact support, even their convolutions is well defined, right? And further, if f belongs to some Cn of Rn and G belongs to G belongs to L1 of Rn, implies f star G is as smooth as f. So the convolution basically smoothens our function G. Okay, now let us go to another. I'm just stating the theorems. That's it. So let f be a continuous function, and G be an integrable function, L1 of R implies f star G is continuous. Now let us say we have this is the most important theorem. Say we have a family of modifiers epsilon greater than 0. Family of modifiers. So if f is a function from Rn to R which is continuous and implies the convolution of f star epsilon, which is the modifier function, a convolution of function with modifier function converges uniformly to f as epsilon goes to 0, and if f is basically continuous on a compact support, implies f star rho of epsilon uniformly converges to f as epsilon tends to 0. I mean, okay, both of this appears to the same, but this is uniform convergence and this is pointwise convergence. So this is smoothening kind of a thing, because rho is infinitely, the family of function is infinitely differentiable. What this theorem basically says is that, say that you have a continuous function, you can make it infinitely differentiable by f star, by convoluting with the modifier. Hypothetically, you have this function. This is a continuous function, but this is not smooth, right? So what you do, you convolve with the modifier and you get some function like this. There will be a small curve here and it will be a small curve like this. So this function is approximately equals to this function. So this modifiers helps us to find an infinitely differentiable function which is arbitrarily close to our original continuous function. And that's the crux of this theorem. I have given detailed proofs and everything in the lecture notes, but if you are basically amazed by what these theorems say, you can look into them. Okay. Now again, I let some continuation on the on the operators. So now I'll just give definition of spectrum and resolvent of an operator. So basically last time we have discussed about semigroups with generalized e power 80 that kind of is generated in differential equations. We have generalized the notion of e power at, where A is a matrix, A is a differential operator, A is a PDE, and so on. And then I have given an example where we have a semi group. We solve the heat equation via variable separable method. We have an heat equation, and from that heat equation we get the double derivative of things. So that's an operator A. So now I'm just going to tell something about spectrum and resolvent of an operator, and that kind of helps us. So rho of A is called the spectrum of an operator. So this is the set of all complex numbers such that lambda I minus A is not invertible. And rho of A is equals to all the set of complex numbers such that lambda I minus A is invertible. Now I'll give an example. Say you have a matrix A. So this is an operator. It takes an element from R2 and gives out an element in R2. So now you take this A. So identity matrix minus A is basically 0, 0, 0, 2. So this is 0, 0, minus 2. This is not invertible, right? So for this particular matrix, for this particular A, 1 and 2 are in the spectrum of the operator. So basically for a finite dimensional operators, the spectrum and the eigenvalues are the same. So the eigenvalues of a matrix are basically the spectrum, and all the complex numbers except the eigenvalues are in the resolvent of the operator of the matrix. And now I'll just give an identity. So this identity is kind of similar with what you get in your Laplace transforms and so on. Okay, so this is what the theorem says. If the semi-group T of T be generated by the infinitesimal generator A with a growth bound of the semi-group being m e power omega t, implies we define this operator RL of A, which is basically lambda I minus A inverse of Z, which is basically equals to, if you remember your identities from Laplace transform, this is equals to 0 to infinity e power minus lambda of t into your semi group T of T into Z dz dt. So this is an identity that I am stating directly without proof. Another identity is that limit alpha tends to 0, alpha tends to infinity, alpha into alpha I minus A inverse Z equals Z. See, to understand this limit, so you basically have alpha I minus A, although you don't write an operator this way. If alpha goes to infinity, your A is neglected and you get 1, right? So that's what it is. So these identities I'll use later to prove something called Hille-Yoshida theorem, which basically guarantees the generation of C0 semi-group. We need to discuss all these things to know what is a classical solution, what's a weak solution of a partial differential equation. So okay, so now I'll state another theorem. So now your d of Rn, if you remember, d of Rn are all infinitely differentiable functions with a compact support. So d of Rn is dense in LP of Rn, where LP of Rn is something that I have defined again and again. All such functions such that f of Rn is less than plus. So what this theorem states, what is the meaning of the theorem? So for now, I'm just focusing on giving an intuition rather than proofs of things, because I think we engineers, we kind of need to know what this is about more than the proof. And if God permits and you are into higher mathematics, if you pursue mathematics at higher level, you will understand all the proofs in that. So what this says is that any function that is basically integrable, which has some finite something, although it's very rough in the sense, you can approximate it with a smooth, infinitely differentiable function, yeah, as arbitrarily close as you want in LP norm. So another theorem is that, say if again you have the family of modifiers and let f belongs to LP of Rn. So the convolution of the modifier with the function uniformly converges to the function if f is compact in LP. Now we state a theorem. So now say basically we can basically the infinitely differentiable functions are dense in all the integrable functions. So any function that is integrable can be made infinitely differentiable by convoluting with the modifier. Okay, so now I define a distribution T mu of f to be f of x minus mu. So there is just a simple theorem that says that limit mu goes to 0, f minus T mu of f in LP now, this goes to 0. And another important theorem, so let phi be an infinitely differentiable function with a compact support, and let rho I be perturbation in the ith row in Rn. So phi minus th e phi by h rho goes to dou phi by dou x1. So basically it is phi of x1 so on till say xi on minus phi of x1 so on till xi minus hei comma 0 by hei. If hei is very small, you basically get the differentiable derivative of the ith row. So that's what this theorem says. Okay, so basically we had to do all these things to understand what's the solution of the PDE. So now we come to the main crux of the program. So now I have stated all the theorems. So it's okay if you don't actually remember the theorem statements. I'll be recollecting them when and while. Okay, so now I'll just talk about the fundamental solutions of a PDE. So in our first class, I told that PDE need not have a unique solution, right? So, there are sometimes when the heat equations gives some kind of solutions that are not physically reliable, and similarly I have basically given Burger's equation where the solution of Burger equation may not be smooth, may not be differentiable, but still satisfies the solution and so on. To generalize the notion of solutions of the PDE, now we have started to generalize the notion of solutions of PDE. So now we define operator L. So L is equals to mod alpha is equation such that A of alpha into D of alpha. So this is basically a differential operator. I have written differential operator in abstract sense. So now I'll just give an example of this. So let's say you have A of 2, 0 dou square by dou x1 square plus A of 1, 1 dou by dou x1 dou x2 plus A 0, 2 dou square by dou x2 square. So this is an example of a Laplacian operator. So what does, now we define what's a distribution solution. Say for an S belongs to some is a distribution on Rn, and we look for a solution T which is a distribution such that L of T equals S. So this is something called distribution solution. So distribution is something that generalizes the notion of function, and this kind of gives us distribution solution. We are basically trying to generalize the solutions of PDEs. So this is something that I have written in an abstract way. But so let us take an example. So let L be the differential operator and S be the distribution of Dirac delta function. So all of us know that d by dx of the Heaviside function h of x is the Dirac function. So h of x is the fundamental solution of this particular distribution equation. Okay. Now let us go to a good example. Now let us take a Laplacian operator. Basically Laplacian operator is most popular, and most popular in the sense this kind of is the most used differential operator in the realm of physics. Whether you take the heat equation dou T is equals to del square U, or the wave equation dou square is equals to del square U, or the Schrodinger equation. So if you remember the Schrodinger equation, dou square by dou T square is equals to del square phi plus 2m by h bar square into E minus u of phi. So this is the Schrodinger equation. So basically in the realm of physics you find the Laplacian operator coming left and right. So let us try to understand the fundamental solution of the Laplacian operator. So now I basically claim that u of x is equals to 1 by 2 pi log mod x is the fundamental solution of Laplacian operator on Rn. So Yeah, proof of that. So firstly we check if u is locally integrable. So to show, firstly we have to show that u is a distribution. To show that u is distribution, it should belong to L1 loc. From the previous in previous classes, I have proved that any function in locally integrable functions is basically a distribution. So b of 0 comma a of is basically equals integral b 0 to a times log mod x. Now I just change this in the polar form, 0 to 2 pi integral 0 to r log r dr d theta. So as r goes to 0, this particular inner term goes to 0. So this is basically always integrable. Now we have to show that u is harmonic. So basically harmonic in the sense that it has to solve the Laplacian operator. So now basically what do we have to show? That let phi belongs to an infinitely differentiable function or with a compact support. And now we need to show that integral r of n u del phi dx equals to phi of 0. So this kind of has some laborious proof which will go forward. So now integral of omega of u del phi equals integral omega epsilon plus integral omega minus omega epsilon times u times del phi. So I'm just taking an annulus strip, right? I'm just taking an annulus strip of radius r. Okay. Which is equals to and you just go through some change of integrals and then what you get up is this. You just change order of integration and you get this particular, and you have to use the mean value theorem, dou phi by dou r into epsilon comma theta d theta this 1 by epsilon d by dr of integral of some term. So this term goes to 0 and this term goes to 0 as epsilon tends to 0. So basically you have that this satisfies the fundamental equation, fundamental solution. Okay. Now let's go to Fourier transform. So now I'll start defining the Fourier transform. So now right now we understood what the solution is and we are trying to build the solution space. So now I'll define Fourier transform and then construct something called Schwartz space, and from Schwartz space we go to Sobolev space. And basically Sobolev space is something that we need for our optimization or machine learning algorithms. So let f belongs to it is Lebesgue integrable, and the Fourier transform f hat of epsilon is basically defined by integral over the entire domain e power minus 2 pi I x comma epsilon, this is the inner product, into f of x and dx. Right. So now we'll just start with the well-definedness of the Fourier transform. Mod of f hat of epsilon is less than or equals to integral Rn. The modulus of this function is 1, so it is just mod f of x dx, which is basically locally integrable, hence the Fourier transform is well defined. So I'll just state a theorem directly. So what I say is that the Fourier transform is uniformly let f be a locally integrable function. So now f hat of epsilon is uniformly continuous in Rn. So this is something that I am stating without proof. It's kind of simple, but just we have to subtract it and then we will have an upper bound. So now I'll just give some identities that we get from our Fourier transform. So your Ey is basically here. If you have studied Fourier transform or Laplace transform, it's just a right shift operator. This is one identity, and then Ey of f hat of epsilon e power minus plus 2 pi I epsilon by f hat of epsilon. The second identity. If lambda is greater than 0 and g of x is equals to g of epsilon is equals to Fourier transform of f of x by lambda, which is equals to lambda power n into f hat of lambda epsilon. So similarly, okay, so this is one of the important. You convert your functions and find the Fourier transform, which is equals to the Fourier transform of epsilon into g of epsilon. Something that all of us studied in our Laplace transform things. So I'm just recapping all that. Okay. So now I'll just give an example. So now let us try to find Fourier transform of e power minus x square. So your f hat of epsilon equals integral minus infinite to infinite e power minus x square into e power minus 2 pi I x epsilon dx. Which is equals to integral minus infinity to infinity minus e power minus x square epsilon square e power minus x plus I pi epsilon whole square, which is equals to e power minus pi square epsilon square into integral Rn times e power minus x plus I pi epsilon square. Right. So this entire thing, if you remember, integral of e power minus x square on the entire domain is e power minus pi epsilon square root pi. So this is the Fourier transform of e power minus x square. So this kind of leads to our notion of what's called a Schwartz space. These are functions which are infinitely differentiable, and the derivative of these functions decay very fast. So just look at them. Once you take Fourier transform of e power minus x square, you will end up with e power minus pi square epsilon square. So these appear to be dual spaces of each other. So basically Schwartz space consists of all functions such that if you take the Fourier transform of it, it should lie in that space. So something like span of e power minus cx square, it kind of looks like a Schwartz space. So for today I'll end this lecture. Next class we'll just explore more on this Fourier transforms and so on. Classes have been somewhat discrete these days. I'm taking class on one day and not on other. So from tomorrow onwards I'll take class every day. Okay. With that I'll just end the lecture.